record. Okay. Lecture 10, lidocaine, and some percent yield mechanism. This is actually hard to explain with slides, so I will draw them out. And it should pop up. Yep, we got it. So, lidocaine. We have two reagents. Okay. So lidocaine, we can approach. We have part A and part B, and part A reacted with the analyte, aniline, and with the acetyl chloride. Yeah, acetyl chloride. And we also have this. Can anyone tell me that why we have to react? Oh, you can see my drawing?
No.
Oh, sorry.
Neither.
How about now?
We can see it now.
Okay, nice. All right. So this is our lidocaine, and then we have three of this reagent. And can anyone tell me that why in part A we have to react with aniline with acetyl chloride instead of reacting with acetyl chloride and the diethylamine first to make this part? And okay, actually I have to explain it. So the main reason is that if we want to make that one to here, this is SN2. And SN2 attack requires a high, the activation energy is actually really high. And meanwhile, the left-hand side, in case Dr. Rudick is asked why, because that one is more electrophilic. This is the hot spot to have reactions or nucleophiles to attack. And this reacts with the carbonyl center really nicely in room temperature. And if we do that, we will actually synthesize this will be here. It will be protonated. And by treating it with maybe sodium hydroxide, it will remove the hydrogen. But regardless, if we do that, we will have this, which is way different than the molecule we want on the left-hand side, which is this aniline. And therefore, we proceeded the experiment by having aniline reacting with the acetyl chloride. By utilizing this really hot electrophile spot.
I'm not quite sure how to help you with that.
Alexa. And for the time shake, you guys can work out the mechanisms by yourself and follow through the mechanism that was in the lecture notes. But at the end, it will produce our analyte. And HCl gas because we kicked this chloride out. And then I can move back to my slide. Keep in mind we have a HCl being generated. Yeah, right, this one. You guys can see the screen of my slide, right? Okay. So because we generated HCl, and the aniline can actually react with HCl and forms NH3 plus Cl minus. And this is soluble in water or insoluble in water? I think it's insoluble in water. Yeah, it was insoluble. And by treating it with sodium, so it looks like that. It will change this to this. Plus, and then OAC. That one is actually soluble in water, which is noted in lecture notes. And that's why when we added sodium, NaOAC is able to get our product more pure by removing this impurity, because this one is also insoluble in water. We need a way to remove this by converting to something that's soluble in water, and which is removed by vacuum filtration in the experiment with water. And everything else is the same in the grading. And consider a scale up procedure. So one thing here. Once we made our analyte out, and I think it was part of your lecture quiz as well. Like when the reagent is 1:1, why the yield is 50%? And the main reason to that is because whenever your lidocaine is out, it also forms a HCl gas or aqueous, which is bonded to water. And diethylamine can react with HCl gas and forms this. The pKa of this one is actually higher than this one. So this low pKa, very high. And because of this feature, and this one is no longer nucleophilic enough, essentially, whenever you make one lidocaine out, you make one HCl, which makes one of your reagents non-reactive. And therefore, it was cut by half. You lost half of your reagents, and that's why the yield is 50%. To make that up, you can choose 1 to 2, but if you really want to ensure that all of your reactants are limiting reagents are reacted, it was used 1 to 3. Just to make sure that all the lidocaines are being made out, or the amount of lidocaine you want to make is there. And then back to the question. I'll probably just work through 2 or 3 of this and then move on to NMR. Okay, I got my pen. So to the crude of the bottom class, a reflux condenser, write down the emission. Okay, theoretical yield is 9 grams. What one of toluene you should use? So toluene. This was the original recipe. And toluene was used as 30 millimeters against where's the products? Okay, so we know that the limiting reagent is our analyte. So we should have 0.024 moles of the lidocaine. And that one corresponds to how many grams of lidocaine? This is lidocaine. That'll be 5.6 grams. 62 grams of the lidocaine. And we want to scale it up to 9 grams. So how many moles of the lidocaine will be made? We do the reverse, 9 divided by its molar mass. And that'll be 0.038 moles of the lidocaine. And we know that the moles of the lidocaine is the same as the moles of the anandide. And for we can set up a ratio. 0.038 moles of the analyte corresponds to X moles of toluene. And for 0.024 moles of the analyte, we need how many millimeters of the toluene? $30 millimeters. So we just have to solve X. And you guys can do that.
So explicitly speaking, what are the mole ratios when dealing with the lidocaine synthesis?
So we assume that it's 1 to 1, theoretically. But the actual is 50%. 1 to 1, 100 yield theoretically. But the actual is 50%.
And when you say 1-to-1, you mean 1-to-1 with the limiting reagent, right?
1-to-1 of the reagents only. That's what I mean by 1-to-1. And if I say if the question asks 1-to-1 of the product and the reagents or the limiting reagents, then yeah.
Yeah, but I'm trying to, is it like one will have 2 mole?
Oh, sorry? I missed it. What did you say about the 2 moles?
No, I was just trying to say, is it like with the ester synthesis where the acid will be, for every 2 moles of acid, you'll have 1 mole of alcohol? I'm asking like what the relationship is between the 2 reagents.
Yeah. So say the ester we are making these experiments we're done in this course is 1-to-1 of the acid and alcohol. But the recipe calls for like 1-to-2 because we want to have some axis to drive the shifted equilibrium to the right. And for 1-to-3, other than shift the equilibrium to the right, we also have to make up the loss of the diethyl amine when the HCl was generated. So theoretically it's 1-to-1, but there's also other cases that we might encounter, and that's why we want to use 1-to-3. But after all, we know that this one is the limiting reagents because not only that, I think this is multiplied by 3, right? Yeah, the mole ratio used here is 1-to-3. And the minimum we want to use is 1-to-2. It's kind of messy here. So we know that this one is the limiting reagent because it's higher than both of our 1-to-1 and 1-to-2. Again, if it still confuse you, then please let me know. And did anybody solve out what how many millimeters of the toluene you should use by setting up the ratio? Yeah, 48 millimeters. And that should be the same in the answer sheet, I hope. And you guys can always refer back to the slide I included. I believe it's the scale up of the ester. Yeah, you guys can pretty much follow this recipe here. But down here we have to switch to toluene. And this is the same as before. Like why the percentage was 50%. And this question asked, yeah, why do we use NaOAC? Because we want to make sure that the side products is soluble in water. And the extraction theory. Extraction for the lidocaine is kind of complicated. So if you follow through the charts, I will use the lecture note actually. And the question asks as what's the best extraction or the solvent used to extract lidocaine. And here we use HCl. So with adding HCl, the lidocaine is actually getting protonated and it's being separated out of against the analyte, which has a similar structure. This one is not reactive to HCl. And this one is, because this one is acidic. This one is basic. And that's when you can react. And then get separated out. And to remove the chloride, we add sodium hydroxide, which deprotonated the hydrogen and forms a salt. And water. And so that's why the answer choice for this one should be toluene. Oh, sorry. This one is actually HCl because this one is basic, and we want to perform acid-base extraction. And which of the following statements about the lidocaine synthesis is true? So of course, to move on to part B, we have to remove the aniline out. That's true. Diethylamine is soluble in water and toluene, so extra washes are required. Yep. This one was in the lecture notes. Because for diethylamine, sorry. I believe the equilibrium constant was like 0.6-ish. So that means that it can stay in 60% is in water. The other 40% is in toluene. And by washing it through with water 4 times or more, we can drive more of the diethylamine, unreacted diethylamine, into the water layer. And this way we can isolate lidocaine out of diethylamine. After shaking the reaction mixture and water in separatory funnel, lidocaine is in the bottom layer. Lidocaine is on the bottom layer. No, lidocaine is soluble in toluene. It's only soluble in water after HCl is reacted, after it's treated with HCl. Acetic acid and sodium acetate catalyzes the equilibrium reaction. Yep, this one is true. This is in part A. Yeah. This one is in the lecture notes. Yes. It asks which one is the answer will ask which one of the following statement is true. But this one is not true. C is not true, by the way. This one is correct. And it is not necessary to use an excess of diethylamine in the reaction. That's not true. because if we use 1:1, it will be 50%. And for amine is soluble in water and toluene, so extra washes of water are required to isolate. Want to make sure it's kind of true. Unreactant must be removed and before reacting. That's true. That's spring 2020. Question number 9. Oh, actually, it's not to catalyze the reaction. It's just a solvent to dissolve the compound. This one is actually true. Yeah, acetic acid in lidocaine synthesis is just a solvent. For E, it's not true. Not true, because 1:1 will be 50%. Use axis, we can increase this up. This is just a solvent, not catalyst. Toluene will be in lidocaine will be in toluene layer. So that one is not true. Unreact aniline before reacting with. This one is true. And that one must be removed too. Actually, I'm not too sure about this one because this too seems reasonable for me. But I definitely know that this one is true because it participates in both toluene and water, and it needs extra washes to remove diethylamine. And then for the last one, same idea. We treat it with sodium hydroxide. Sodium acetate. So let me move to this. And I need the lecture slide. So the purpose of sodium acetate is, I believe, is somewhere here. Yeah. B is true, and A, I'm not too sure about that. So for this one, it was in the lecture note that diethylamine it can participate in both toluene and water. So that's why you need multiple washes to remove pull the continue extract diethylamine out of toluene. So you can have them away out of reach from lidocaine. By having more waters being washed out. More and more C will stay in water layer, so that's why you can purify a lidocaine by removing all of the diethyl ether. And to another question in the chat, what does the sodium acetate do? The sodium acetate the main purpose of sodium acetate is convert one of the side products, which so one of the side products was is insoluble in water, and we want to make that soluble in water. That's why we add sodium acetate. That is the main reason. And then for Y, we have to remove all of them out because maybe this one is true. I don't know why this one is kind of confusing. That one is soluble in toluene. And we just want to make sure that this one is out. So we only have this left and reacts with this in order to make lidocaine. And we don't need anything else that was left before. That is my explanation. This one is from lecture quiz, I believe, yes. And we pay attention to the functional groups. This one's nonpolar. This one's nonpolar too. And basic. This one's acidic, which means that our acid will be really happy to react with sodium hydroxide. And everything else will go to the nonpolar layer. So we have 2 and 3. And our 2, we have a base, and we are reacting with an acid. That means that we will have our 2 down here. And 3 is nonpolar, it's not reacting with our base or acid, so that's why it's on the top. And then we extracted our benzoic acid into base form, and that's why it's soluble in water. That will be our benzoates. And then the benzoates is being treated with, so this is basic. This is acidic, which is nice because we can have our acid-base extraction. And what's gonna happen is that it's gonna protonate it back to benzoic acid. And we know that from experiment 2, benzoic acid is non-soluble in water. So that's why it will stay right here. pH, which is 1. And D will just have salts and water. And which solution and which letter will be benzoic acid after extraction? Yeah, it will be C. And that will be the end of lecture 10. And you guys have any questions? We're using sodium acetate. So the side products can be soluble in water, which isolates away from our products. This one is a base, and we want to extract it with an acid. That's why we use HCl. This one I know B is true, A is kind of true. We have to remove stuff from A in order to proceed the procedure in part B. And this is just some questions from the previous exams.